Hello class, and welcome to the Parallel Circuits video lecture, which you should be completing on page 119 of your interactive notebook. Let's start with a little bit of review. Ohm's law states that the voltage of a battery must be equal to the total current in the circuit times the equivalent resistance of the circuit. So what I have a picture of here is what's called a simple circuit. One battery, one resistor. So things are nice and easy. This voltage equals this voltage. All right, I also know the resistance here, so I can find the current. Nice and simple. Now, things get a little bit more complicated, if you recall, when you have more than one resistor. And for that, we got two big rules. The first rule is the loop rule, which states that all voltage gains in your system along your path must be equal to the total amount of voltage lost by your system. So if this is the path that our current is taking, now I'm going along, I can find how much voltage is lost here, how much voltage is lost here, and how much voltage is lost here. And it's going to add up to be 12. Now if you remember from these numbers, our current is 1 amp. So in this case, this is 5 volts, this is 4 volts, and this is 3 volts. 5 plus 4 plus 3 happens to equal 12 volts, the voltage of the battery. And this works for any single path that we can draw. It just so happens that for this circuit, there is only one path. More on that in a moment. The second big rule that we used to help us out when we got more than one resistor is called the junction rule. And it says, well, hey, if you trace the path of the current, the total amount of current has to stay the same. So if the current splits, so there's right and there's left, the total still has to equal the total. Now look at this though. As I just said, only one path. So there is no split, which means that the current has to be the same everywhere in a series circuit, because there's nowhere else for the current to go. All of it goes through A, all of it goes through B, all of it goes through C. Now, this gets a little weirder when the road splits. So here I have 10 amps coming down the wire, and then there's what's called a junction, or a split. Some of the current goes up, some of the current goes down. Notice, though, that the total amount of current stays the same, because 6 plus 4 still gives us 10. Alright, then the 6 amps comes this way and hits a junction. The 4 amps comes this way and hits a junction. They then recombine together, making 10 amps. Total of 10 amps, a total of 10 amps, a total of 10 amps. Before and after each junction. That is what the junction rule states. Alright, so this means we put all this together. For a series circuit, we can say that the equivalent resistance is RA plus RB plus RC. We can say that Ohm's law states that the voltage of the battery is going to be equal to the total current times the equivalent resistance, which we can find with this equation here. But if I just want to know the voltage lost by one resistor, I do not want to use the total current. I do not want to use the equivalent resistance. I want to use the resistance of that one resistor and the current in that one resistor. Luckily for us, this is a series circuit, which means that the total current is the current through resistor A. So now we can just do some simple algebra and solve for delta VA by taking my total current, which is 1, and multiply it by the resistance of A, which is 5, giving me 5 volts. The voltage lost by A is 5 volts. Now I just want to say that again one more time. Look at these two equations. They look the same. They are not the same. They are both Ohm's law, but the blue one is about the total circuit. It's the voltage of the battery, the full circuit, the current of the full circuit, the resistance of the full circuit. Where the pink one is something else. The pink one is the voltage lost by one resistor only. The current in one resistor only. And the resistance of one resistor only. That was our number one confusion on the lab. All right, but what about if we got this stuff wired in what's called parallel? So we got this wonky setup here. What does that mean? What is going on in this case? Do the rules of the series equations still apply? The answer is no. Here on the left, I have a parallel circuit. Let's break it into its parts, shall we? We have the blue path. We have the pink path. Notice how they overlap. And we have the yellow path. Right here, I have just yellow. Right here, I have just pink. Right here and right here, I got pink and yellow together. Right here, I have just blue. But right here and right here, I have pink, blue, and yellow. So this looks a lot like the junction rule to me. I got pink, blue, yellow. Blue goes this way, I still got pink, yellow. Pink goes this way, I still got pink. Pink and yellow combine to give me pink, yellow. And pink, yellow, and blue combine to give me pink, yellow, blue. This is, in fact, the junction rule. Let's call this current A. Let's call this current B. And let's call this current C. Where this crazy stuff right here is the total current. Where, wait a second, that's current A. And, oh, that's current B. And, wait a second, that's current C. In a parallel circuit, the total current can be found by adding up the current in each individual resistor. They add up to give you the total current. All right, now let's look at the loop rule. Here we have the voltage of the battery, and I don't even know what's going on here, so I'm going to ignore that. I'm just going to look at the blue path first. All right, voltage of the battery is there. The loop rule states that any voltage gained must be equal to any voltage lost. That's right. I'm saying that the voltage of the battery must be equal to the voltage lost or used by resistor A, because there's only one path. Let's look at this path. Same story. The voltage given by the battery must be equal to the voltage used up by resistor B, because they share a path. What about over here? Same story. The voltage lost or used up by C must be equal to the voltage of the battery, because if you go on the path, any voltage you gain must be equal to any voltage you lose. All right, which means we got that there, and that there, and all of these things are equal. This is only true for a parallel circuit. All right, so let's slap all of that together. Here we have for a series circuit. All right, well, the voltage of the battery is equal to adding all of the voltages used up, and all of the currents are the same. The equivalent resistance is you add all the resistances up. These two equations. All right, pretty self-explanatory. For a parallel circuit, these two equations are still true. If I care about the total circuit, I use this. If I care about just one resistor, I use this. But here's how things are different. Where in a series circuit, This was the relationship for voltage. In parallel, that is my relationship for voltage. All of the voltages are the same. And the total current is adding up all the little currents. Very nifty. Huh. But how do I find equivalent resistance then? Do I still just add them all up? Well, no, I don't think I would. Because look at this. Here I have, to use our numbers from before, say this is 12 and this is 3, right? So that means that we got a voltage loss of 12 here, a 3 ohm resistor means a current of 4. Let's say that it's another 3 ohm and a 3 ohm. So 4, 4, and 4. That gives me 8, 9, 10, 11, 12 amps as my total current. Wait a second. If I have a voltage of 12 and a current of 12, that means I have an equivalent resistance of 1. Even though each resistor has a resistance of 3. That can't possibly be right. But it is. If we were to do some crazy algebra, I could set all the voltages equal to each other using the bottom equation. I could then rearrange the Ohm's law equation to give me I equals delta V over R. Substitute in all my I's into this equation, and I could solve for my equation to give me equivalent resistance. Or I could just give it to you. Let me explain this. This says that if you have three 3 ohm resistors wired in parallel, the equivalent resistance will be 1 over 3 plus 1 over 3 plus 1 over 3. All right, 1/3 plus 1/3 plus 1/3 equals 3/3, which is 1. Then I have to do 1 divided by that to get the equivalent resistance. 1 divided by 1 is 1. Confused? You should be. That's pretty weird. We got an example problem later to help. So, here is the definitive page. Everything you need to know about a parallel circuit all in one spot. I told you I had an example problem. So here we have a 12-volt battery with a 3 ohm, a 4 ohm, and a 5 ohm resistor. What is the equivalent resistance? Well, the equivalent resistance equation states that we're going to take 1/3 plus 1/4 plus 1/5, and that will give us 1 over equivalent resistance. Okay, 1/3, that's about 0.33. 1/4, that's about 0.25, and 1/5 is 0.2. Add all those up, you get 0.78. Is that the equivalent resistance? No. No, it is not. I now need to do 1 divided by 0.78. And that gives me my equivalent resistance, which is 1.28 ohms. Now, this next thing is always true, so listen carefully and write it down. In parallel, the equivalent resistance is always smaller than the smallest resistor. I'll say that again. In parallel, the equivalent resistance is always smaller than the single smallest resistor. The single smallest resistor here is 3 ohms. My equivalent resistance is smaller than that, and that will always be true. All right, so we've done that. Yay, equivalent resistance. Woohoo. What is the total current in the circuit, though? Well, we have this nifty equation. If we know the voltage of the battery, we do, and we know the equivalent resistance, we do, we can find the total current. So we do. 12 volts divided by 1.28 ohms is going to give me, I round up, 9.4 amps. All right, cool. That's fancy. What's the next step, Mr. Salzo? So now that you know the total current, I mean, that's nice. I want to know, though, the current in each individual resistor. How are you going to do that? Well, Mr. Sazzle, you should say to me, we know Ohm's law, which states that the voltage lost by one resistor equals the current in that one resistor times the resistance of that one resistor. So, since we know the voltage used up by A, it's 12, because they're in parallel, and we know the resistance of A, it's 3, because I said so, I can divide them to get the current in A, 4 amps. I can do the same thing for resistor B, give me 3 amps. But I can do the same thing in resistor C, give me 2.4 amps. All right, sanity check. I told you that if I add up current A, current B, and current C, I should get the total current. Do I? What is 4 plus 3 plus 2.4? Okay, well, 4 and 3 gives me 7. 7 and 2 gives me 9. 9 and 0.4 gives me 9.4 amps. So yes, my math is all consistent. It all works out. Next step. So what is the power of each resistor? Well, at this point, you know the current in each resistor, you know the resistance of each resistor, and you know the voltage lost by each resistor. So we're just going to use this equation. The power of resistor A is going to be the current in A, which is 4 amps, times the voltage used up by A, which is 12 volts, giving me a power of 48 watts. I can do the same thing for B, 36 watts, and for C, give me 28.8 watts. Now remember, watts is the joules per second, which means it's the brightness. So which light bulb is going to be the brightest here? This one. Resistor A, the one with the smallest resistance, will burn brightest. The end.